Hello everyone, thank you for attending my talk. I'm Sili. I'm happy to share my topic today. My topic is Wi-Fi security from 0 to 1. First of all, please allow me to introduce myself. I am a security researcher at Huawei Root Lab. I focused on software vulnerability research. Below are my Twitter and GitHub links. If you are interested, you can follow me. Next, I will show my topic. This is the outline of today's presentation. First, I will introduce some background knowledge about Wi-Fi security, including the basic knowledge of Wi-Fi protocol, some previous research on Wi-Fi security, and finally, I will introduce the security risks faced by the Wi-Fi protocol stack. Then, I will take real text format firmware and its Linux software drivers as an example to introduce the remote attack surface of the Wi-Fi protocol stack, as well as the code review and vulnerability analysis technique of the Wi-Fi protocol stack, and introduce several discovered vulnerabilities to help you understand it. Then I will introduce the implementation of Wi-Fi Hunter and several vulnerabilities discovered by this tool. Wi-Fi Hunter is a further for Wi-Fi protocol stack. It will open sourced on my GitHub after the meeting. Next, I will briefly introduce the local attack surface of Linux Wi-Fi driver. Finally, I will summarize the speech. Next, I will introduce some background knowledge of Wi-Fi security. First, I will introduce three main reasons for studying Wi-Fi security. First, as shown in the picture on the left, with the development of technology, Wi-Fi is used in more and more scenarios, such as mobile phones, IoT devices, smart cars, and so on. Second, the Wi-Fi protocol stack is complicated and needs to process complex data structure and state machine, so it is prone to vulnerabilities. Third, once the vulnerability is successfully exploited, the attacker can achieve a zero-click attack and gain access to users' network data. For example, the picture on the right shows Google Project Zero attacking iPhone through a Wi-Fi vulnerability. Next, I will introduce some previous research on Wi-Fi security. The content in the green box is a classical case of remote control device through the Wi-Fi protocol stack vulnerability. The vulnerability used in these three cases are all heap overflow vulnerabilities, which are caused by passing some variable length data structures of the Wi-Fi protocol stack. The gray box in the table are for typical Wi-Fi fuzzing research. They both have a similar idea, that is, manually model the Wi-Fi protocol stack and then perform targeted fuzzing on the vulnerable area in the Wi-Fi protocol stack. For example, various information elements in the Wi-Fi frame. Here I highlight the research of OWFuzz. OWFuzz is a Wi-Fi protocol fuzzing tool developed based on the Open Wi-Fi platform. After research and comparison, I found that OWFuzz should be the best Wi-Fi fuzzing tools in the open source community. Wi-Fi Hunter introduced in this speech is based on OWFuzz. By analyzing the previous security research, we can find that the remote attack surface of Wi-Fi protocol stack is mainly located in the following two aspects. First, when the software passes various TLV data in the Wi-Fi frame, if the data length is not checked carefully, it may cause overflow vulnerabilities. Common structures that are prone to vulnerabilities are information elements, nested TLV structure in the information elements, such as ePort structure, Wi-Fi P2P attribute, and some TLV structure customized by some vendor. The second risk is that in the Wi-Fi protocol, when device need to transmit large amounts of data, the data needs to be transmitted in fragments, and the peer device needs to aggregate the fragmented data frames. Vulnerabilities are prone to occur in the process of aggregating fragmented frames. In addition to the remote attack surface, there are some local attack surface for Linux Wi-Fi driver. The Linux Wi-Fi driver generally provides some configuration interface with the user space. If the driver does not carefully check the data from the user space, it may cause security vulnerabilities. Currently, Linux Wi-Fi driver can provide the interface for user spaces through WEXC or CFG 80211. The figure on the left shows the structure of information element, and the figure on the right shows the P2P attribute. They are all typical TLV structure in Wi-Fi frame. Next, I will introduce some knowledge of Wi-Fi protocol stack. The left picture shows a typical AP-STA Wi-Fi network structure. This is the scenario when we use a Wi-Fi router to access the internet at home. The AP in the picture is our router, and the STA means the various devices that access the Wi-Fi router through the Wi-Fi protocol, such as mobile phones, laptops, and so on. The figure on the right shows the structure of the Wi-Fi protocol stack. The Wi-Fi protocol stack can be roughly divided into the physical layer and the data link layer, and further subdivided into PHY, PLCP, MAC, LLC layers. The MAC layers is responsible for most of the logic of the Wi-Fi protocol stack, such as data process or Wi-Fi frames. Protocol state, machine management, and most Wi-Fi vulnerabilities in its history are located in the MAC layer. Therefore, the focus of availability mining should be the processing of MAC frames. Next, we look at the structure of the Wi-Fi physical frame. The physical frame composed of PLCP header and its frame data. There is a length field in the signal field of PLCP header, which represents the length of the data behind the frame header. After the Wi-Fi chip receives and passes the physical layer data, it will pass the MAC layer data to the up-layer software for processing. A MAC frame consists of a frame header and a frame body. There are several important fields in the frame header. The frame control field stores a lot of important information, including the type of frame, whether it is a fragmented frame, and so on. There are also several address fields in the frame header, which are used to indicate the sender, receiver, and BSSID address of the frame. The frame body is followed by the frame header. As shown in the figure, it is the structure of a beacon frame. You can see that Wireshark identifies the frame type, receiver address, and sender address. Different types of MAC frames have some difference in the format of frame body. The general format is composed of some fixed length structure and some variable length information elements. The picture is an association frame. You can see its frame body is composed of fixed and tagged parameters. The tagged parameters represent information elements. Fixed is the fixed length structure. The red mark in the figure is an SSID IE, which represents the SSID to be connected. You can see that the length of the IE is 5 and the value is 37 lab. And you can see that IE is followed by a supported race IE. Let's take a look at the interaction between STA and AP when a STA wants to join the AP's network. First, STA will send a probe request to the AP. Then the AP replies to the STA with a probe response. Then STA sends an authentication request to the AP. Then AP replies authentication response to STA. Then the STA sends an association request to the AP. Then AP replies with an association response to the STA. After the association is completed, the data frame interaction will start, and the equal authentication is carried out in the data frame interaction. In this process, the information exchanged between STA and AP is mainly carried by various IE. Next, I will take a real text firmware for MAC network card and its Linux driver for soft MAC network card as examples to introduce the remote attack surface or Wi-Fi protocol stack, as well as the audit and analysis technique of Wi-Fi protocol stack, and introduce several previous disclosed vulnerabilities. First, let's take a look at the current hardware and software architecture for Wi-Fi network card. The left picture shows the architecture of two types of Wi-Fi network cards. Currently, Wi-Fi network cards can be divided into full MAC and soft MAC network cards. The difference between the two is the location of the MAC layer processing logic. The processing logic of the MAC layer in the full MAC network card is located in the firmware code of the chip, which means that the processing of the information elements in Wi-Fi frame and the protocol state machine are located in the firmware of the Wi-Fi chip, while the processing logic of the MAC layer in the soft MAC network card is located in the driver code. The figure on the right shows two implementations of the Linux soft MAC driver. The difference between the two is that the MAC layer on the left uses MAC 80211, while the MAC layer on the right is implemented by the chip manufacturer. MAC 80211 is the Wi-Fi MAC layer implemented by the Linux kernel itself. Its code quality is relatively high, and it is difficult to find vulnerabilities in it. However, the MAC layer implemented by the manufacturer is often prone to vulnerabilities because it has not been strictly audited. Next, let me introduce the ideas and the technique of audit the code of Wi-Fi protocol stack. This technique are also applicable to audit the code of other similar protocol stacks, such as BLE protocol. Code audit is actually a manual data flow analysis. The process is as follows. First, we need to find the code responsible for processing internal data, because vulnerabilities are caused by improper handling of internal data. Common methods for locating data processing code are as follows. First, we can search some keywords in the code, such as probe, beacon, and other keywords related to the Wi-Fi protocol. In addition, we can also use some common function name keywords, such as path, handle. Second, we can find the target code according to the Wi-Fi protocol specification and the processing logic in the code. Third, we can quickly locate the data processing code by analyzing the root case of history vulnerabilities. In addition, by analyzing history vulnerabilities, we can also know the things that are prone to bugs when handling the Wi-Fi protocol, which help us to quickly find some similar vulnerabilities. After locating the data processing code, we need to check the data transmission and process in the code. In the process of tracking data, we need to pay attention to whether the operation of processed data will cause vulnerabilities. There are two scenarios that are prone to vulnerabilities. The first is the processing of various TLV data, such as information elements, epoch frame structure, and some nested TLV structures. The second is the arithmetical operation in the code. If the data involved in the calculation is not checked, an integer overflow may occur. Next, I will take RTL 81958 as an example to introduce how to start with history vulnerabilities, and then analyze the code flow of its firmware, and finally discover new vulnerabilities. In February 2021, VDO team released several vulnerabilities in the Wi-Fi protocol stack of RTL 81958. After analysis, I found that these vulnerabilities are mainly caused by not checking the data length when processing some TLV data structures in the Wi-Fi frame, such as the epoch frame. The right picture in the slide is one of the bugs. You can see that when the length of epoch message is greater than the length of temp buffer, RTL mem copy will cause overflow when copying data to the temp buffer. The RTL 81958 is a real-text format Wi-Fi card. The code for its Wi-Fi protocol stack and the developer's code will run on the chip as part of the firmware. The protocol stack code is located in the static library of the SDK. Users can use SDK to develop their up-level applications, and this static library in the SDK are linked into a firmware, which is placed in the RAM of the chip to run. The following figure shows some static link libraries in the SDK. The libwlan.a contains most of the code of Wi-Fi protocol stack, such as passing information elements, handle, protocol state machine, password verification, and so on. Next, I will take CVE 2020-9395 as an example to introduce how to analyze the vulnerabilities of RTL 81958. In order to improve the efficiency of analysis, I first extract the .o file in the o.a file, and then use GCC to link all the .a files into a SO file. And then I use IDAR for analysis. After I download the SO file, we jump to the vulnerability function, that is the CheckMeek function. The content of the function after the vulnerability is patched is shown in the right figure. The logic of the function is as follows. First, it copies import data in the Wi-Fi frame to a stack buffer. Then it calculates the hash of the data. Finally, it will verify the meek field in the import frame to ensure that there is no error in the data, as shown in the red box in the figure. The patched function adds a check at the beginning of function to ensure that the data length is less than 0x200 bytes, so as to avoid stack overflow. By analyzing the context of vulnerability function, we can note that the data parameter of the CheckMeek function actually points to the 802.1x part of the Wi-Fi frame, and the second parameter is the length of the data. Therefore, we can note that the data points to the externally controllable data, and then we can check back to the up layer from the CheckMeek function to check the use of the data, so as to locate the code related to the Wi-Fi data processing in the program. Then I looked for the column of the CheckMeek function and tried to find some new vulnerabilities by checking the use of the data parameter. Then I found the code shown in the figure on the right. You can see that in the line 6, data plus 18 is assigned to the import key message received member of the info structure. Then it will call CheckMeek function to verify the meek value of the data. After the verification is passed, it will call DEC-GDK to decrypt some of the data. Finally, memcopy will be called to copy the data of the import key message ICV to the out-stack buffer, but the size parameter of memcopy is directly taken from import key message received. If this value is too large, it will lead to stack overflow vulnerability. After continuous upload backchecking, we can gradually master the structure of the code. The code flow chart of the firmware when it processes Wi-Fi frames as follows. First, when Wi-Fi network card receives a Wi-Fi packet, it will trigger an interrupt, and then the CPU will call RTL8195A receive tasklet function, which is used to process the received Wi-Fi packet. This function will call receive func. Receive func is the entry function of packet processing. Receive func first call receive func prehandle, which is mainly responsible for processing management frames such as probe, beacon, and so on. Receive func post handle is used to process data frames. When data frames involve fragmentation and aggregation, the function first aggregates the fragmented data frames and then calls RTW receive indicate packet to process data frames. After analysis, the main work of this function is to pass the data related to import frames. Vulnerabilities mentioned above has appeared in this function. Let's take a look at another heap overflow vulnerability when firmware passing information element. When the function passes a specific information element, it will enter line 14 in the figure for process. It first allocates memory to new IE. The memory size is the length of IE minus 2. Then, when copy memory to new IE, the length of the copy data is IE length minus 4. The structure of PIE is defined on the left side of the slide. All members in the PIE are obtained from the Wi-Fi frame. When the length of PIE is 3, only 1 byte of memory will be allocated to new IE in the line 14. However, when copying memory in line 19, 0xFF bytes of data will be copied due to the integer overflow, which leads to a heap overflow vulnerability. In addition to some new memory vulnerabilities found in the firmware, an interesting thing was found in the process of help Realtek to fix these vulnerabilities. Next, I will share it with you to avoid a similar situation in the future. On the February 3, 2021, the video security team disclosed some vulnerabilities in RTL8195A and stated that the vulnerabilities are completely fixed in April 20. On February 4, 2021, after analyzing the vulnerabilities and the patch for this, I discovered some additional vulnerabilities and submitted the vulnerabilities to Realtek by GitHub. And on February 26, 2021, Realtek stated that the new submitted vulnerabilities was fixed in SDK. And a few months later, on August 16, I analyzed the latest version of the SDK again and found that some of the vulnerabilities I submitted before have not been fixed. On the September 7, after repeated communication with Realtek, it was found that the builder did not merge the patches for the vulnerability. On September 7, Realtek released the latest SDK which fixed the vulnerabilities. We can learn from this method that we should do well the regression test after patching vulnerabilities, and the version management needed to be standardized. Next, I will introduce how to audit the Linux softmaker driver of Realtek, and introduce some previous vulnerabilities. The reason I researched Realtek's softmaker driver was that I needed to perform Wi-Fi fuzzing in the 5G band. After some searching, I finally found the RTL 8812AU wireless network card. Then, when debugging some bugs, I analyzed its driver code and found some vulnerabilities. RTL 8812AU is a softmaker network card. It can use monitor mode in 2.4G and 5G frequency bands, and its price is relatively cheap. In addition, the core logic of the driver is similar between different Realtek network card models. So the vulnerabilities found here can affect most Realtek softmaker network cards. By observing the directory structure of the driver and searching keywords in the driver code, we can find the code responsible for passing Wi-Fi data and then check the data processing flow. Finally, we can get the code flow of the driver, which is shown in the figure. When the driver is loaded into Linux kernel, it will register a interrupt handle in the kernel. When the hardware of network card receives a Wi-Fi frame from the L interface, it will trigger the interrupter, and then the kernel will call the interrupter process function to handle the packet. After interrupter process function performs some simple process on the data, it will call receive buffer to receive frame for specific data processing. If the monitor mode is enabled on the Wi-Fi card, receive buffer to receive frame will call receive frame monitor, send the data packet to the user space process, and then the function will return. When the monitor mode is not enabled, it will call receive function pre-handle to process the management frames. For example, on probe request is used to process probe request. If it is a data frame, it will enter receive function post handle. This function first decrypts the data frame. And if it is a TDS frame, on TDS function will be called. Otherwise, fragment aggregation of the data frame will be carried out, and finally it will call receive process MPDU to process the aggregated data frames. By analyzing the source code of the Realtek driver and compared it with MAC 80211 in the Linux kernel, we can get that there are two main parts of the driver that are prone to vulnerabilities. First, some basic types of frame of the Wi-Fi protocol will be passed in the driver, such as probe, beacon. This is similar to the working mode of MAC 80211, but because the code for processing these frames in the Realtek driver is developed by itself, so the code quality should not be as good as MAC 80211. The second risk is that the Realtek driver will also handle more complex protocols such as TDIS and Wi-Fi P2P. In the standard MAC 80211 driver, the process of this protocol is handled by a user space process, which name is WPA supplicant, so it will introduce a new attack surface to the driver. After analyzing the code flow and determine the potential vulnerability locations, the next thing we need to do is to carefully analyze the Wi-Fi data processing logic in the code, especially the various memory operations, to find the security vulnerabilities. And shown in the figure below, it is a heap overflow vulnerability caused by the program when passing the supported IE in the situation response frame. The size of the supported REST info AP is 16 bytes. When the length of IE is greater than 16, it will overflow. As mentioned earlier, in addition to the basic management frame, the Realtek driver also processes TLS and P2P protocol-related data. Let's take a look at the vulnerabilities when Realtek driver processes Wi-Fi P2P protocol. The Wi-Fi P2P protocol mainly transmits data through action frames, and a small part of the data is also transmitted through probe, association, and beacon frames. And shown in the figure is a brief Wi-Fi P2P protocol interaction process. First, device B sends a probe request to device A. Unlike the normal probe request, the request will carry a P2P IE, which is used to transmit some P2P-related information. Then device A will respond a probe response packet. This step is called the device discovery step. Next, group owner negotiation will be carried out. In this step, P2P packets of GoNGO type will be used for interaction, and the information exchanged between the devices will be transmitted through various attributes in the P2P IE. After the GO negotiation is completed, the interaction similar to the AP mode will be carried out, including sender, authentication, and association frames. The only difference is that Wi-Fi P2P will carry P2P IE in these frames to transmit Wi-Fi P2P related data. On the previous page, I introduced the introduction of the Wi-Fi P2P protocol. Here, we will take a look at the structure of P2P IE. In Wi-Fi P2P, the information in the P2P protocol specification is transferred between devices through the P2P information element. The structure of P2P information element is shown in the left figure. First, its element ID is 0xDD, which means it is a vendor IE. And then through the OUI and OUI type field, it is specified as a P2P IE. The OUI type is followed by an indeterminate number of attributes. The structure of attribute is shown in the right picture. Each attribute has one byte attribute ID, which indicates its type. Then there is a length of 2 bytes, which represents the length of the attribute body. Then there is the content of the attribute body. Therefore, we can know that P2P IE actually embed variable length attribute structure in the basic IE, and the passing of such nested variable length structure is often prone to problems. Next, let's take a look at how Realtek passes these attributes. The picture on the left is a P2P IE captured by Wireshark. There is a P2P capability attribute in the IE, and the length of the attribute is 9. On the right is the code for passing P2P capability attribute in the Realtek driver. The code flow is as follows. First, it calls RTW get P2P IE in the 9.3 to search the P2P IE in the received Wi-Fi frame. Then it called RTW get P2P attribute content in 9.5 to find the attribute whose attribute ID is P2P capability in P2P IE. And the content of the attribute will be copied to cap ATTR, and the length of the attribute will be saved to ATTR content len. Let's take a look at the process logic of the RTW get P2P ATTR content function. The code is shown in the figure. First, in line 6, it calls RTW get P2P attribute to find a specific attribute in P2P IE and return the starter address of attribute. The length of attribute is stored in ATTR length. Then, if buffer content is not empty, the content of ATTR will be copied to buffer content, and the length of the memory copy is ATTR len -3. Note that it is not checked whether the copy length is greater than the length of buffer content. If the length of the attribute is greater than the size of buffer content, it will cause overflow. Next, I will introduce a heap overflow vulnerability when driver processes the fragmentation of data frame in the Wi-Fi protocol. If the length of the transmitted data is greater than the MTU, the frame needs to be fragmented, and then the fragmented frames need to be aggregated to at the receiver device. The frame fragmentation mechanism is implemented through the more fragments and the fragment number fields of the MAC frame header. The figure shows a fragmented data frame. The more fragments in the header is 1, which means that there is fragmented frames that need to be transmitted after this frame. Fragment number is 0, means this is the first fragment. The structure of the last fragmented frame is shown in the figure. If more fragments is 0, it means that this is the last fragmented frame. When the receiver device receives this frame, it needs to start frame aggregation. Next, take a look at how Realtek drivers merge the received fragmented data frames. When Realtek receives a fragmented data frame, it will store the fragmented frames in a linked list. And then, when it receives the last fragmented frame, it will merge the fragments. The function of receive frame defrag is to merge the fragmented frames in the linked list. The specific process is as follows. First, it assigns the head node of the linked list to PFHDR on the next line. So PFHDR points to the memory that stores the first fragmented frame. Then the linked list will be traversed later, and the data of all remaining fragments will be copied to the memory of the PFHDR. When the frame size after fragment aggregation is greater than the size of the memory pointed by PFHDR, a heap overflow will result. Since PFHDR is the memory located by SKB buffer, we can overflow to the SKB shared info behind SKB buffer. And showing the figure is the log when kernel panic after the overflow is triggered. Next, I will introduce the implementation of Wi-Fi Hunter. Wi-Fi Hunter is a Wi-Fi protocol fuzzer implemented based on the OW fuzzer with some optimization. OW fuzzer is the best open source Wi-Fi fuzzer, but there are some limits. First, I tested many network cards, including RT5370, AR9271, 8812AU, and so on, but only RT3070 can work successfully. But it will also lose some packet. And there is a more important reason is that RT3070 and Open Wi-Fi only support 2.4G frequency band. Due to the packet loss and some bugs in the implementation of protocol interaction in OW fuzzer, the interaction speed is relatively slow. Third, data mutation strategy is relatively simple. Only one mutated IE will be generated for each packet. 4. It don't support fuzzing Wi-Fi P2P, but in October, OW fuzzer added some code. It seems that Wi-Fi P2P fuzzer was added, but I have not tested it. 5. The POC record and reproduction mechanism is relatively simple. 6. After one crash is found, fuzzer will exit. We can't continuously fuzzing the target. Wi-Fi Hunter is a Wi-Fi protocol fuzzer developed based on OW fuzzer. Its main optimizations are as follows. First, it optimizes the send and receive mechanism of Wi-Fi frames, which make it supporting 5G band network cards such as RTL 8812AU and MT7612U. Second, it optimizes the protocol state machine and data mutation strategy to improve the speed and efficiency of fuzzing. Third, it supports fuzzing Wi-Fi P2P. Fourth, it optimizes the POC recording and replay mechanism, crash detection mechanism, and support continuous fuzzing. OW fuzzer uses the interface encapsulated by aircraft NG to send and receive Wi-Fi data frames. After some research and experimentation, I found that when I use Leo PCAP's interface to send and receive packet, AR9271, 8812AU, and other network cards all can be used for fuzzing. The specific modification is actually very simple. That is, change OSDP read packet to pcap loop or pcap next, and change OSDEP send packet to pcap send packet. When capturing data packets in the air for analysis during fuzzing, I found that many packets have been retransmitted, resulting in a slower fuzzing speed. After researching, I found that Wi-Fi uses ACK mechanism. If the ACK frame is not received, the sender will retransmit the frame, which will affect the fuzzing speed and effect. And shown in the figure, 5E87 address first send a probe request to 36E0. 36E0 represents the probe response frame to the 5E87, but since 36E0 does not receive the ACK frame from the 5E87, it will constantly retransmit the probe response frame. Then the question is why my network card does not send ACK frame to the target device, and how to send the ACK frame to the target device. After some research, I found that there are two ways to solve these problems of packet retransmission. The first method is that we can use the MAC address of the network card itself as the MAC address of the fuzzer when starting fuzzing, so that when the hardware of network card receives the Wi-Fi frame whose receiving address is its MAC address, it will actively send ACK frame to the target device. This process is all in the network card hardware and has nothing to do with the driver. The second method is to use a network card that supports active monitor mode, such as MT7612, and then we can use monitor mode to send ACK frames directly in user mode. This table is a list of Wi-Fi network cards as I have tested. The third column indicates the price of the network card in RMB. Among them are two network cards. Let me introduce them in particular. RTL8812AU is the most suitable network card for fuzzing. It supports send and receive packet in the monitor mode of 2.4G and 5G frequency bands. MT7612U is the only network card founded to support active monitor mode, but its program is that when the monitor mode is turned on, it cannot send packets in the 5G frequency band. Therefore, I recommend use RTL8812AU for fuzzing. Next, let's introduce the optimization of Wi-Fi Hunter's mutation strategy for information element. We know that each IE in the Wi-Fi frame is stored sequentially. This layout makes it more troublesome for us to make a mutation, especially if we want to modify the length of IE and change the position between the IE. So the plan I take is as follows. First, I pass all IE in the Wi-Fi frame and use a linked list to organize all IE in the frame. Then we mutate the IE. It mutates the IE nodes in the linked list, such as byte flip, IE length change, and so on. After the mutation is complete, we will serialize the linked list and put it in the Wi-Fi frame. During the serialization, we can also modify the order between each IE. The previous page introduces the general IE mutation strategy. For some special IE and data, in order to improve the fuzzing efficiency, it is necessary to make customized mutation, such as ISN IE, P2P IE, and ePro data structure. And shown in the left figure, some variable length structure are nested in ISN IE, such as pairwise chipper shield, authentication key management, and so on. And shown in the figure on the right, there are also some variable length structure in the ePro frame data. Let's briefly introduce how I fuzz Wi-Fi P2P protocol. First, I need to implement the Wi-Fi P2P protocol interaction and then make a customized mutation to the data in the P2P frame, mainly the attribute in the P2P IE. The mutation of attribute is similar to the previous mutation strategy for information elements, so I won't repeat it here. Next, I will introduce the optimization of Wi-Fi Hunter in crash detection and POC recording and reproduction. After analysis, OW fuzz currently only support ping the target machine to determine whether the target device is alive. And once a crash is found, the fuzzer will only save the last packet sent by it, and then the fuzzer will exit. The implementation of Wi-Fi Hunter is as follows. In terms of crash detection, Wi-Fi Hunter adds a new mechanism to detect whether the device is crashed by monitoring the Wi-Fi frames of target device. And when the device crashes, Wi-Fi Hunter will save the test case and then wait for target device to restart for continuous fuzzing. In terms of POC recording and replay, Wi-Fi Hunter will start a new thread to record the Wi-Fi frames interaction between the fuzzer and the device under test. When replay does the POC, Wi-Fi Hunter will replay the recorded frames in the interactive order to ensure that the vulnerabilities can be reproduced. The following figure is a test case of a POC. You can see that the protocol interaction between fuzzer and the device under test is recorded in the POC. This is a demo video of fuzz Windows Wi-Fi driver. It can be seen that Wi-Fi Hunter will not exit after detect the target crash, but wait for the target device to start again and then continue to fuzzing. This is a demo video of POC reproduction. After the development of Wi-Fi Hunter, I used the Linux and Windows driver of RTL88112AU for fuzzing, and finally found the following vulnerabilities. It found 3 bugs in the Linux driver that I didn't find by audit driver source code, and it found 4 bugs in the Windows driver. The tested Windows driver version is as follows. This is the latest driver provided by the network seller. As shown in the figure, it is a bug in the Linux driver. The bug is that in line 7 and 13, we unlock a spin lock twice, resulting in an infinite loop of the kernel. There is another bug discovered by the fuzzer. TLV is from Wi-Fi frame, so it is controlled by user. In line 6, it calls kmalloc to lock memory. Its parameter is length. When the length is 0, kmalloc returns 0 PTR instead of 0. So it will pass the check on the line 7. And then when the memory is accessed in memcopy, it will read data from address 0x10. It will cause the kernel to panic. Next, I will briefly introduce the local attack surface of Linux Wi-Fi driver. In Linux, user usually configure the network card through the iwconfig or iw command, such as setting the MAC address of the network card, allowing the network card to scan the Wi-Fi hotspot, and so on. These operations are actually communicated with the Wi-Fi driver of the kernel store system calls, and then the kernel driver will control the hardware to complete some specific configuration in the current Linux kernel. The user mode and the Wi-Fi driver can communicate through WEXT or CyberWeek 80211. WEXT actually uses the NDO dual control callback functions, and CyberWeek 80211 is implemented based on the netlink mechanism. Regardless of the mode, when the driver is processing data from user mode, it may cause vulnerabilities if the data is not carefully verified. The Realtek driver provides two implementations of the interface. I guess it is to support different versions of Linux kernel. On the left is the registration structure of WEXT. Here, we only need to pay attention to the callback function of NDO dual control. The callback function registered here will be called when the user space process performs IO control on the network card. On the right is the callback function of CyberWeek 80211. When the user space process sends a specific type of netlink message to the network card, the corresponding callback function will be called. By searching these two structures in the source code, we can find the entry function for process user mode data. And then, according to the kernel calling convention, we can select found vulnerability. Next, I will introduce two simple bugs. This is a heap overflow vulnerability when WEXT interface process user mode request. First, the line 4 of the code. Memory will be allocated according to the P length. The data of P is controlled by user mode, so the user mode can control the length of A. And then on the next line, it will copy data to A. Copy size is the size of global data. When the copy size plus 0x30 is greater than the length of A, it will cause heap overflow. There is a heap overflow vulnerability in Realtek's CyberWeek 80211 interface when process user mode request. The cause of this vulnerability is similar to the previous one. First, it uses A length to allocate memory in line 8, and then use B length when copying the memory below. If B length is greater than A length, it will cause heap overflow. Next, I will summarize this research. Through this research, I have learned that first, vulnerabilities are prone to occur in TLV data parsing and aggregation of fragmented frames. Second, the patch management mechanism needs to be improved to ensure that the vulnerabilities are rarely fixed in the actual released version. Third, fuzzing can find some unacceptable bugs. Fourth, the Wi-Fi driver should try to use MAC 80211 to handle the Wi-Fi protocol instead of implement it yourself. The good news is that the new generation of Realtek soft MAC network card began to use the MAC 80211 to handle the Wi-Fi protocol. This is just an idea when I was analyzing the Wi-Fi protocol, and it has not been verified. We know that there is a length field in the physical layer protocol of Wi-Fi that indicates the size of the data behind the PLCP header. Will there be some network cards that handle it incorrectly, leading to unacceptable behavior? And I would like to thank Realtek's security team for efficiently and promptly handle this security issue and for their professional conduct of communication. Thank you, everyone. That's about with all my speech.